Hello friends, welcome to lecture series on essential mathematics for machine learning. In the last few lectures, we have seen some of the basic concepts of optimization, basically convex optimization. We have seen that what convex functions are, when an optimization problem is said to be convex programming problem, and based on that what are the various properties or various algorithms are there. Okay. We have also seen some numerical search techniques for optimization like steepest descent method, conjugate gradient method, etc. So, in this lecture we will see the Python implementation on optimization basically, that if you have some convex optimization problems, how we can use Python to find out the optimal solution directly. So, for that we will use one package basically, that package is basically CVXOPT, that is basically convex optimization. So, what it is basically? It is a software, package for convex optimization based on Python programming language. Okay. It is very easy to use and directly it gives the optimal solution of a given convex optimization problem. So, the simplest convex optimization problem we know that it is a linear programming problem. Linear programming problem, as we already discussed also, is the one in which objective function as well as all constraints are linear and it is trivially convex. Now, if you want to find out to write a Python code of this linear programming problem, how we can do that? So, first of all we should understand the template or the format of writing a linear programming problem in Python using this software which is CVXOPT. So, what is that? So, for linear programming problem the format of writing this is basically minimum of z is equal to C transpose x subject to A x less than equal to b. So, this is the main format of writing a linear programming problem in this. I want to say that suppose you have this problem, suppose minimum z equal to is a 2 variable problem, suppose 2x1 plus 3x2 subject to say x1 plus x2 greater than equal to 2, 2x1 plus 3x2 less than equal to 12, x1 greater than equal to 0 and x2 greater than equal to 0. Suppose you have this simple linear programming problem and you want to write this problem in this format. So, that means what is C here? So, this can be written as 2 3 and this is x1 x2. So, basically this is your C transpose here. So, C will be basically a column vector or a column matrix. Now, all constraint must be less than equal to type. So, you have to first multiply this constraint, the first constraint with -1 to reduce this into less than equal to type. So, this inequality will convert into minus x1 minus x2 less than equal to -2. This is already negative. So, I mean less than equal to. So, there is no problem over here, 2x1 plus 3x2 less than equal to 12. Then minus x1 less than equal to 0, minus x2 less than equal to 0. Okay. So, what is A here? A is this matrix. What is A here for this example? Now, for this example A will be what? A will be minus 1, 2, minus 1, 0, minus 1, 3, 0, minus 1. This is your A. Okay. What will be B? B will be the right hand side. B is minus 2, 12, 0, 0, this is your B. Okay. What is C? C will be your 2, 3. Now, you will write all these things in using Google Colab or this Python and then you can find out your optimal solution. So, let us see how we can find out the optimal solution of this particular problem using CVXOPT. So, first of all I will import solvers and matrices from CVXOPT, I mean convex optimization this software. So, from CVXOPT import matrix or and solvers. Okay. First of all, we do this, then we will feed A equal to what A we will be having. A is basically 4 cross 2 matrix. So, what that matrix is? So, we write matrix and then it is the first column is what? -1. Now, in here all the values are floating type. So, we write dot 0 here, then it is 2 dot 0, then -1 dot 0, then it is 0 dot 0. This is the first column, and the second column is what? Second column is -1 dot 0. So, we write in this bracket. So, it is -1 dot 0, then 3 dot 0, then 0 dot 0, then -1 dot 0, and it is a matrix form. So, it is a matrix. So, if you want to see this matrix, so you can print A. Print A will give this matrix. So, this is this matrix -1 2 -1 0 first column, second column is -1 3 0 -1. Okay. Now, if you want to see the size of this matrix, that also you can see using A dot size. Okay, size also you can see. Size is 4 2, 4 rows 2 columns. Okay. This simply to check that whatever matrix which we have written is correct or not. Then similarly you can feed matrix B, then B equal to what? B equal to matrix, it is what? It is -2 dot 0, then 12 dot 0, then 0 dot 0, and that 0 dot 0. Okay. Then C you will write. C is what? C is again a matrix, and this is what? This is given by 2 dot 0 and 3 dot 0. So, first of all you feed all the entries, all the given matrix capital A, B and C. Okay. It is understood that it is of the type Ax equal to B, and you are minimizing C transpose X. Okay. Now, you want to solve it, this LPP you want to solve. So, you will use solve equal to, and then you use solvers which you have already imported. Solver is for this is LP, solver dot LP, and you can write C, A and B. Okay. Then you can simply print this solve. Okay. And then variable x. Yeah. So, you have to find the optimal solution here. So, print solution for variable x. So, what is the answer? Let us see. So, answer is basically you can see that this cost is declining, and it will at 5th iteration it go to 4. Okay. And the optimal solution which you have found is 2, and it is 5.38 in 10 raised to -7, which is nearly 0. So, that is 2 comma 0 is the optimal solution in this case, and the value of the objective function is 4. Okay. Now, suppose you want to reduce the number of iterations, you want to see that what is the solution you are finding in, suppose in second iteration. So, how you can do that? So, you can write here options equal to presses maximum iterations, basically it is max iterers colon. Suppose you want to see solution after 2 iterations. So, let us run it. So, this is the value you are getting here after 2 iterations. And what about 3 iterations? Similarly, you can reduce the iterations, you can increase or you can find out the value of the solution after 2 or 3 iterations, any number of iterations you want. So, for this you find the optimal solution. Okay. Optimal solution is what? Optimal solution is the same, it is 2 and it is 0.00053. Okay. So, in this way, if you are having a linear programming problem, that you can find out using this simple code, and also you can restrict the number of iterations. If you want 2 iterations or solution after 3 iteration, you can restrict also using this command. Basically, in this solver.lpp, it is using interior point method to find out the optimal solution of linear programming problem. Okay. This is the simplest example, this is the simplest method I think, simplest problem for which we can find out the optimal solution using CVXOPT. Okay. Now, how can we solve a quadratic programming problem if it is convex using this technique? So, let us see. So, I already told you that a quadratic programming problem is one in which the objective function is quadratic and all constraints are linear. So, for QPP basically, if you talk about QPP, for QPP objective function is quadratic and all constraints are linear. And it will be a convex programming problem if basically the matrix involved in the objective function is positive semi definite. What is that matrix? So, first of all I am writing the format of the QPP in which we can write it in Python using CVXOPT, and then I will tell you that when this problem will be a convex programming problem. So, the format is this, you can write a minimum of 1 by 2 x transpose p x plus q transpose x subject to g x less than equal to h and a x equal to b. So, this is the format of writing QPP using CVXOPT. Okay. Now, this problem is convex programming problem if this matrix P involved here is positive semi definite. This we have already seen in our previous lectures. Suppose take one example and how we can find P, Q, G, H, A and B. Let us discuss using that, and then we will use Python that how we can find out the optimal solution of a given convex QPP. So, suppose you have this problem, minimum of f equal to, suppose x1 square plus x1 x2 plus 2 x2 square plus 3 x1 4 x2 subject to say 2 x1 plus x2 equal to 1, x1 greater than equal to 0 and x2 greater than equal to 0. So, first of all how you will find objective function in this format. Okay. So, objective function here is what? Objective function f here is what? F is x1 square plus x1 x2 plus 2 x2 square plus 3 x1 plus 4 x2. So, this can be written as 1 by 2 x1 x2, then it is you can write 2, then it is 1 1, this is 4, this is x1 x2. Because basically 1 by 2 is also here. So, you have to write in this way, because if you divide it by 2 this matrix then and multiply these 3, then you will get back this quadratic term of this objective function, then plus 3 4 x1 x2. So, now this is your capital P and this is your Q transpose. Okay. Now, from the constraint this is equality type constraint. So, A will be what? A will be your, in this case A will be 2 1. Okay. A is 2 1 and B is what? B is only 1. Now, this can be written as minus x 1 less than equal to 0 and this can be written as minus x 2 less than equal to 0. So, these two constraints can be rewritten as in the form of G. G will be minus 1 0 0 minus 1 okay, and less than equal to H. H will be what? 0 0. So, this is your A, this is your B, this is your G, H, P and Q. So, as we did for linear programming problem, in the same way we will feed these P, Q, G, H, A and B in Python and then we will use a solver which is solver.qp to calculate the optimal solution of QPP. So, let us see how we can use it to find out the optimal solution. So, I am copying the first line over here. So, then you will feed capital P first, capital P equal to matrix, capital P is what? 2.0, then 1.0, okay. Then the second one is 1.0, 4.0. So, this is your basically matrix P. You can also see that what this matrix is by simply see print P also. So, yes, it is 2 1 1 4 fine. Now, you will similarly feed Q. Q is what? Q is again a matrix and it is what? It is 3.0 comma 4.0. This is this Q. Okay. Then G, capital G is equal to matrix, then it is minus 1 dot 0 0.0 and in the second one it is again we will use 0.0 comma minus 1.0. This is your G matrix. Now, what is left? H. H is equal to what? Matrix and this is what? This is 0.0 0.0 okay. Then capital A matrix, capital A is matrix. Now, it is first column is 1, second column is also 1. So, it is 1 and 1 and it must be floating type here. So, it is 1.0 and it is 1.0 and this is again in matrix form. Then B is there, B is a matrix of 1 cross 1. So, B is matrix, we can write in matrix form. So, it is 1 only. So, we have written capital P, Q, G, H, A and B. Now, we will use solver. So, you can use solve equal to solvers dot qp okay, and that you will feed all the values P, then Q, then capital G, then H, then capital A, then P. Okay. So, it is P, Q, G, H, A, B, yes, fine, and then you simply print solve as we did earlier self dot for the optimal solution x. Now, you can run it. Oh, it is 1.0, yes. So, you can observe that the value of cost is decreasing and the final optimal solution which you have obtained is this, okay, for this problem. So, basically this is how we can find out then optimal solution of a convex QPP. Okay. It is very easy, you have to simply know about the format. If you know the format, then simply you can insert the values of the matrices P, Q, G, H, A and B and simply use solvers dot QP to find out the optimal solution of a given convex QPP. So, not only LPP or QPP, if you are having some non-linear convex optimization problems also, so that also we can solve using CVXOPT. Okay. So, we have seen that if we are having simple convex optimization problems like linear programming problems or quadratic programming problems, then we can use Python with CVXOPT for finding the optimal solutions of such convex optimization problems. Not even this, if you are having unconstrained optimization which is convex or some other nonlinear convex optimization problem, then also we can use CVXOPT for finding optimal solutions. Thank you.